Hello, everybody. When I think of coming here, I think I should have learned more than un homme de pair, de fils et de saint esprit. I should have learned a little more than Vater unser, and I speak Bronx English, and maybe that isn't so good either. At any rate, I'm glad to be here, and to me, this is a very interesting subject because it involves so many fields. And as you see, I put up all these notions of what it involves, and when you talk about this, you have to talk about history, and then you have to talk about philosophy, and then you're talking about ideas that, like privacy, that are very controversial. Then you talk about interesting ideas that spin off the subject of mathematics, and you see that the impact of cryptography enters into the political domain that we are dealing with right today. And so it's a very interesting subject. I might say a little bit about how I got into it. So first I studied mathematics. And when I studied mathematics, we studied some algebra that had to do with cryptography. Then I went into the military, and I was an airborne telecommunications officer and got involved with a group in the United States Air Force that was called the Foreign Technology Division. And my job was to watch Soviet computer technology. And so I was watching that, and I was involved in a lot of cryptography when I did that. And then when I was at the university, I began teaching cryptography maybe 20 years ago. And I've taught it many, many times. And I'm amazed at how far it has come, both in the capabilities of giving students problems and challenging work to do, as well as how I've had to revise the course every time I teach it. I'll be talking, as I indicated a little here, from an American point of view. And so in some ways, I'm the ugly American. I don't take enough consideration of the rest of the world when I do this talk. So I was hoping the professor who was working in cryptography would be here, and he might challenge me on a few things, or at least enlighten me on a few things. So in the United States, there's this fellow, Herbert Yardley, and he's working goes in as a telegraph operator. And he's a very bright guy, and he's working sort of in the State Department in the United States. And he begins to, on his own, translate some of Woodrow Wilson's secret messages. Now, the secret messages in this time is not being done, or are not being done, by complex cryptography. They're just codes that one word is replaced by another word. And but on the other hand, he's very insightful, and when they start to see that he knows something about breaking this code when he's not supposed to know anything about that, they take him seriously, and they put him in a position that he begins to do military intelligence. In the United States, leading up to World War I, the sinking of the Lusitania was a very big thing. You all will be listening to the 100th anniversary of all this in the next few years. And I'm sure we're going to find out things that we didn't know before. But one thing we know about the Lusitania is that the Germans advertised in the New York Times that the Lusitania was carrying weapons and weaponry, and they advised people who were getting on the Lusitania not to do so, because they considered it a ship of war. So when the Lusitania was sank, yes, America was angry and mad and all of that, but they didn't go to war about that particular issue. So in Germany in 1916, the Germans appointed this fellow Zimmermann, and we'll run into another Zimmermann later on. And Zimmermann, his job was to keep the United States out of war, but he wanted to get back to the unrestricted submarine warfare activity that was going on at the time, the warfare that he stopped after the United States raised hell about the sinking of the Lusitania. Now, my good friend Winston Churchill, who, if some of you saw the movies about the First World War and the way that the British brought in the New Zealanders and the Australians and tried to establish a second front in Turkey, Winston Churchill was the cause of that catastrophe. Lots and lots of Australians and New Zealanders got killed. And so he came back with his tail between his legs, but he always was interested in secret messages, and so he got involved in what Great Britain called Room 40, which was there. Another word that's used in this discussion is black chamber. It's a word meant to describe looking at secret messages. So Zimmermann sends this telegram, and this telegram, even though it's really not crypto, looks a lot like what crypto does. And it looks like it's got these sequence of digits. And this telegram is picked up by the British, and the British start working on the breaking of that code, and they succeed in breaking that code. Now, the interesting thing about this code is in the sense today when we hear it, it's a little preposterous, but nevertheless it's what Zimmermann wrote, and he wrote it to the President of Mexico. So it says a little bit. We intend to begin on the 1st of February unrestricted submarine warfare. We shall endeavor, in spite of this, to keep the United States of America neutral. In the event of this not succeeding, we make Mexico a proposal of alliance on the following basis: make war together, make peace together, generous financial support, and understanding on our part that Mexico is to reconquer the lost territory in Texas, New Mexico, and Arizona. The settlement in detail is left to you. You will inform the President of the above most secretly, so soon as the outbreak of the war with the United States of America is certain, with the suggestion that he should, on his own initiative, try to get Japan to immediately join in the same fight against the United States. So not very many Americans, and probably not very many Europeans, are aware of that kind of thing. Well, first of all, whenever you break a code of another country, you don't want the country to know that you broke their code. So Great Britain is stuck in Room 40 with this problem. We broke the code, but how do we inform the United States about it so that they will indeed go to war against Germany, but not let Germany know that we broke the code? So they go through a lot of ruse to do this, and they find a way of getting into Mexico City's Western Union Station and getting a copy of the telegram and using that as their explanation of how the code was broken. But this takes a long time. So this is, over here on the left, is the code that's broken. And you see, you just have numbers being equal to some German word or some American word. So it's not a encryption, it's a cipher. It's just a code book that says this number means this English or German word. And that was the way a lot of codes were sent at the time. So these people in Great Britain were trying to, as I said, not let the Germans know about this breaking of the code, but they, by finding the code in Mexico City, they were able to say, well, now this is how we did it. So in February, they tell the Americans, and the American Congress, of course, is furious about this, following on the Lusitania, and they're ready to go to war, but the congressional people say, I don't believe it. And for the first time in my memory, our friend Zimmerman, he says, I did it. I sent it. I don't remember any news story where anybody admits anything anymore, but Zimmerman said we sent it. Now I'd like to understand really what was the background of all that, why he admitted it, and why that happened when that isn't usual State Department-like parlance. And then finally on April 6th we go to the war. So the war starts 95 years ago. Wilson got elected he kept us out of war, that's how he got elected. These are the dates. And the U.S. gets going on cryptography because they begin to see that breaking secret messages is something that needs to be done. So at any rate, right at the end of the war, this fellow Cheribus, he invents the Enigma. And he thinks of it and sends it for sale as a banking and business kind of activity. And it was equivalent to Albert's cipher disk, Alberti's cipher disk, and it's called the Enigma. And it's a Greek, German, English, and almost French word, which is interesting that the word has that many origins and is not really translated. And the military did bought the idea of using it, and they were absolutely convinced that it was unbreakable. And here's what Cheribus used in his advertising down there at the last sentence. He said, Cheribus calculated if 1,000 cryptographers, that was his word, each with a captured Enigma, tested 4 keys a minute, all day, every day, it would take 1.8 billion years to try them all. And we still do that kind of advertising about computing in cryptography, and we call that computational security. Not cryptographic security, we call it computational security. So now we move into the Enigma. So here now, the first time in Poland, the Polish people put together a cipher bureau. And they're getting enlightened, and they hire mathematicians from a university to come to work on it. And Marian Rejewski is the first person to be heading up that Enigma breaking activity. And of course, you know where Poland is and how they're worried about Germany. And so along with Jerzy Rosiecki and Henryk Zygalski, they break the Kriegsmarine and Reichswehr Enigma code in 1932. And they're starting to read other intelligence by 1933. By 1939, they have a great deal of history in breaking German code. And the Great Britain, GB, Great Britain's General Code and Cipher School comes to Rejewski, and they're amazed at what Rejewski has done. And so they come there in 1939, just before the origin of World War I, and they take away with them all the work that the Polish did. So when you look at that, you have to look at the genius of Rejewski and his colleagues and what they did to try to break that code. But like in all cryptography, and in all stories you talk about cryptography, you never know what the truth is. Was it the genius that broke it, or was there a spy that let you into something? And in this case, there's a spy involved, a German spy, and he gives them the wiring diagrams for the Enigma. So that helped them a great deal. But Rejewski and his crew developed a machine called the bomb, and there's various pronunciations of that. And the argument is, and it is a word, it's a dessert, that you take watermelon and you fill watermelon with ice cream that apparently was popular in Poland at the time. So that's what they say was the origin of the word. But it's not clear what the true origin of the word was. But at any rate, when the British come there, they take all the work that Rejewski's team did, but they don't take Rejewski and his crowd to Great Britain. He goes to work in France and is not really recognized by the British as contributing very much. Well, now we come to our hero in computer science, whose 100th anniversary of his death was this year, Alan Turing. And Alan Turing just finishes his PhD, and he starts to work on the breaking of the Enigma. And he develops a mathematical approach that builds on Rejewski's ideas, and he builds a better bomb, a bomb that is more automated and more sophisticated than Rejewski's work. Now, I've been there. If you ever get a chance, you should go to the, first you should go to the Kensington Museum in London, the Science Museum. Their exhibit on Babbage is fascinating. And then if you get out to Bletchley Park, about 50 miles outside of London, they always give the story of this Enigma in more detail than I can. They hired about 10,000 people by advertising in the British journals to get people who were classicists, chess players, mathematicians, and scientists. So I don't know how your keyboard goes, but in the United States it's QWERTY, and the German keyboard is QWERTZ. And the rotors were the way it worked, and you're going to essentially put in a letter, and you're going to have these rotors put in. The rotors are put in an order that are described by the manual that tells you how to do it, and they're twisted a little bit. Each one is twisted a little bit, again, by a manual telling you how to do it. So when you put in a letter in, another letter comes out, but it goes through this encoding process which changes the letter. And the more rotors you have, the harder, of course, it is to break. These rotors are removable, and they're, as I said, they're part of the code was which rotor went into which slot. And there were about 30,000 Enigmas manufactured. They go out on eBay now for upwards of $15,000. This is a field version of the Enigma. And this is a picture of the British version of the Polish bomb, and that's more or less working in the code and cipher school that I was talking about. So then Great Britain begins to run out of capability, manufacturing capability, so they get the American firm known as NCR, or National Cash Register, and they get into the manufacturing of these bombs, and again they make it more sophisticated, and it's working faster in helping to break code. There's this is always the case in science and in cryptography especially, that people are competing with one another about who did what first and who did how much. And so there's a big discussion. Did the Polish, are they really responsible for the beginning of the breaking of the code? Are the British with Turing and company, are they responsible? Well, how much did NCR add to the breaking of the code process? So that's a continuing argument among those who are historians. And so this is the bomb mock-up at Bletchley Park today. And at the same time, Great Britain understood that this was a computational problem, and so they started building a machine called the Colossus. And just in the last 5 to 10 years, Bletchley Park got that running again. Back over here, this is a paper tape reader. That was my first computer that I worked on, was a Burroughs 205, which had a paper tape on it. And I would see myself at night splicing paper tape after the paper tape spun too fast and broke, and try to create little holes that make the thing work again. But at any rate, they have this paper tape working, and this was a secret development on their part. And it's still, I shouldn't say it's still, they got it reworking again. So then in the American cryptography scene, you have these characters that come on the scene. Yardley was a character. If you read some of his books, he's a character. But he's a very smart fellow, too. But Friedman is smart, and he comes from Russia, and he gets working for a fellow by the name of George Fabian, who's trying to prove that Bacon wrote Shakespeare's plays. And I have some of the work of that lab of proving that, and unbelievable levels of effort trying to prove that Bacon wrote Shakespeare's plays. So he meets Elizabeth, and she's a cryptologist, and she goes to work with him, and they start working for the United States. So in the 30s, he gets assigned the charge of breaking the Japanese code known as Purple. And that's another machine like the Enigma, and it was broken by this team led by Friedman. And the fascinating story about that, again, which you'll be around to hear and probably see hundreds of History Channel-like stories on it, was the time interval where there were this multi-part message that comes through about the Japanese going to attack Pearl Harbor, and the United States is breaking the code faster than the Japanese are reading the code in their offices. But there's a gap, probably, I'd say 8 hours. And if it was 8 hours earlier, it would not have been a sneak attack. So you're going to hear more about that in the next few years, what the truth is behind that story. But anyway, Friedman did an enormous amount of work to do that. And because of this, the Battle of Midway in the United States War and the Battle of Coral Sea, we had a lot of information about where the Japanese ships were, so that our aircraft carriers and the planes on the aircraft carriers knew where to go to catch the Japanese. So Friedman, of course, having this, the United States knowing that Great Britain is breaking German codes, and old Roosevelt and Churchill are scratching each other's back about secrets. They love secrets too. So Roosevelt sends Friedman to Bletchley Park to say, you know, you show me yours and I'll show you mine. So he's trying to tell them what he has done with Purple, and they're trying to get what the Great Britain has done with the Enigma. Now at this time, the Great Britain doesn't trust the United States very well. They particularly didn't like Patton. Patton would talk, General Patton. He would talk, and they didn't want the Germans finding out about all of this, and so they were not anxious to share much, but since Friedman had something, they started giving the United States a little more. So after the war, we start to have the first big change. Prior to the World War II, I have a manual that's a officer's training manual for cryptography, stamped with red rubber stamp saying top secret, top secret, top secret. And it's like an elementary course in cryptography for high school students. But at the time, this is top secret. And the codes were all secret, but they were known by the cognoscenti. The smart people in the world knew about this, but they still kept it, they thought they were keeping it secret. After the war, they began to realize that this isn't the way to do business. What you have to do is you got to expose your code. You got to let the world know what your code is, and what makes for the security of the code is the length of the key. So the key becomes to repeat myself, the key becomes the key to breaking the algorithm. And so NSA first begins as a very secret agency. You can't find it in the budget. Truman was the one that started it, and NSA starts getting more and more forced to be public. If you go out now and look at the NSA site, it's an interesting site, and it talks all about cryptography and the history of cryptography, and they have sections for kids to learn about cryptography and all of that. Now, you never know, it doesn't matter if I'm talking about the Belgian secret agency, or the Israeli secret agency, or the American secret agency, or the German secret agency. Nobody's telling anybody what they know. So you don't know what other people have. You're guessing at what they have. And so the question of how many codes NSA has broken is not, you don't know that. You're just guessing about that, and you're likewise guessing about what the other countries have broken. But you're always sort of approaching the problem with the notion that somebody has broke your code. And if you don't approach it with in that manner, you're naive. The other thing I bump into as I walk around, people tell me, oh, I have the greatest cryptography code in the world. It'll never be broken. And I say, well, who has been, oh, it's secret. And that's what defeats it, because if you don't expose the code to people to try to break it, you have no idea if it's really secret. It has to be tested, and that's what all the modern codes, at least modern up to maybe 10 years ago, do. So the first big code that comes out is called the Data Encryption Standard. And this standard they put out the American National Bureau of Standards, now called the National Institute of Standards and Technology. They solicit candidates from what's called the Federal Register. It's sort of like, we need this software, can you do it for us? And a handful of proposals submitted, and a fellow by the name of Horst Feistel of IBM was the one who submitted a key response to that. Now, Feistel's work is based on calculations and theory done by Claude Shannon. Claude Shannon is a great guy, and he's a good guy. He's not a Bill Gates. He's not trying to make $1 million all the time. He's the kind of guy that down to earth and is a great theorist, and he's responsible for the area known as information theory. In my day, you had to take courses in information theory. That was an essential course, at least in the statistics curriculum. So he gets his master's and PhD from MIT, but he writes his doctoral thesis on population genetics. So he's another character, as I indicate. He's known for writing his unicycle down the hall at night. He published this mathematical theory of communications, which is the foundation of information theory. And then he brings up the controversy. He publishes the theory of secrecy. And I would say he is greatly responsible for turning cryptography from an art to a science. So he continues, when he comes back in '58, he continues to threaten the whole hall by doing his unicycle and juggling. And he's got a whimsical mind, and he's breaking Rubik's Cube puzzles. But at any rate, he's the founder of information theory. And Horst Feistel knows all about this. He comes to the United States in '34, and he's placed on house arrest because he's German and he's smart. And he gets into ciphers at the Air Force Cambridge Research Center. And by the 1960s, he starts to run afoul of NSA. They don't like people breaking codes, except that they break codes. So Feistel finally gets a job at the Thomas Watson laboratory, and interestingly enough, develops what he called the Lucifer system. And so I digress here a little about, this is the paper in Scientific America that brings up this whole controversial business that's with us today. We want security, but we want privacy. It harms the world, and so from many, many years ago, this becomes a controversial issue. So he knew that cipher, of course, that Lucifer cipher couldn't be implemented by hand, so he develops this block cipher. That's what his system is, a block cipher. So you take a batch of plain text and you go through and you generate an equal length of ciphertext. And it's all based on diffusion, where bits and bytes are dispersed throughout the ciphertext such that a single change in one bit affects the position of multiple bits during subsequent rounds. So what you often do is you take a message, you translate it into binary, you change one binary bit, you send it through the DES system, and out comes the encrypted message, and it's altogether different from the one that you put in with the original one you put in. So you see, and then the same thing with the key. You change one bit in the key, and the whole thing blows up. And not blows up, but gets dispersed throughout the translation or encipherment process. So it became this very strong system. It was used by business before it was adopted by NIST. But NSA gets into the business, they reduced the required number of bits in the key to 56 bits. And they forced that. That was a forced political activity, because the people who at IBM wanted the key to be longer. But NSA wanted to be able to break the code. So they apparently had computational capability to break a 56-bit key. So they said, okay, we'll let it go if you have 56 bits. So they do it, and it said that they said they couldn't break it, but I don't believe it. So it was developed, officially became a standard, and it's used throughout the world since 1976. Now, one of the problems with having a single key, like you use it, the same key is used in enciphering and deciphering, is key distribution. And this key distribution is called the key distribution problem. And so, when I was in the military, you'd go down to the dock in New York, and you'd have these gigantic boxes with chains around them, and Air Force and Marine guards with Tommy guns guarding the boxes as they were going on the ships. And they were going to all the embassies and military sites in the world. So you can imagine how much paper was being shipped, and what a fuss they made about all of this. And so that whole effort to get the key distributed was an enormous amount of work. And so it was the same problem with the Germans. The Germans, when they had the Enigma, they had to distribute the key. And the key was which rotors to put in which place, how much to wiggle each rotor. Had something to do with some wire patches that were at the end of the sequence of doing the coding. And they had to get these to all their submarines. They had to get them to all their field officers. And this key distribution problem was an enormous problem. And there's a lot of, not a lot, but there are a few movies about the British jumping submarines and collecting this key book that the Germans had on the sub. Again, it's like Hans Theo Schmidt. If I get the key book, I know a hell of a lot more about what it takes to break the Enigma than if I didn't have that book. And so they were always trying to get the key, the book. And the book was covered with a lead cover. And the instructions to the German officer on the sub was dump that book. That's the first thing you do. Get that book into the ocean. And the British were told, get that book before he dumps it into the ocean. So the key distribution problem is with us for a long time. So I say potential security risk, of course. So I have all these words that I'm sure you know about. You have the word cryptography, and the other word is cryptanalysis. So the right word to use is cryptology. So cryptography is the making of codes, and cryptanalysis is the breaking of codes. So you might think a little bit, if you were in charge of a cryptography group, what would you put somebody, what job would you give them to do first? Break codes or make codes? It's sort of like, I've changed my mind about this. Earlier in my life, when I hired programmers, not the best programmers, I'd always put them testing programs. Now it's just the opposite. My best programmers I'll put to try to test programs. But it wasn't that way in the beginning. So you might debate that with yourself. Which is the harder thing to do? Which is pedagogically the right thing to do to get somebody's mind working on this kind of thing? This is the traditional diagram. It's very much like Shannon's diagram. So you've got some sender with a message. You've got a secret information that you're going to put in. Then you're going to have a security-related transformation. That's what that is. Then you're going to get your secret message. It's going to go over the information channel. Then there's an opponent that's be able to see that message. And then you decrypt on the other side. And sometimes these keys are handled by a trusted third party in the key distribution arena. So these are the words. You've heard me use them. I hope that you picked up on the word, and the notion of secrecy of the algorithm is no longer the idea. If you go out to the NIST site, you'll see the exact description of DES. and the exact description of other modern cryptographic codes. So then, again, you've got the secret key, which is the same secret key, and that's the adaptation of the first diagram. So here then is a graph of the time to break a code. Now, it says 10 to the 6 decryptions per microsecond. It doesn't matter. The point is, the longer the key length, the longer it takes to break the code. But this is all dependent of about the point in time when you're drawing this graph, and it all is a function of how much computational power there is in the world. Clearly, we have many new computer architectures that can break code with high performance computing. And so this chart is out of date the moment you publish it, and it's out of date because I don't know what NSA has. I don't know how much advanced computing they have, and it doesn't matter whether I say NSA, or it doesn't matter whether I say the Israelis or whoever I say. I don't know their computational power. So I don't know how many years it's going to take to break some code, because it's a function of the computational power of the environment. Now, an interesting thing about all this, in my mind, this was a luncheon conversation, is that we think a lot of this activity of breaking codes is a function of, at least today, a function of good skill in number theory. Now, I don't know if you know Ramadan, who came out of India and worked for Hardy in Great Britain, a number theorist, but he was in the field. He wasn't an educated person, but he discovered an enormous amount of number theory without being educated. And Hardy recognized right away how good he was. And he was, you could call him a idiot savant, you could call him a genius, whatever you wanted to call him. Well, since the internet comes out, when I got on the internet, maybe I was one of the first 500,000 maybe that got on the internet. Today there are 2.4 billion people on the internet. Of the 2.4 billion people, are there any Mozarts that are there? That are geniuses that we are now going to find? Are there any Mozarts in cryptography or number theory that are there that are going to discover something? Where do they exist? Are they only in high-powered countries that have enormous computational capability? I don't know about that. What I'm saying to you is that genius is going to crop up more likely in the more people we have on the internet. We're going to find that, and it can come from anywhere. So now, I've mentioned a little more by key distribution. So now I'm moving from single key, I'm moving from single key to public key cryptography. So we have our first, what they called in those days, cyberpunk. So this is Diffie, Whitfield Diffie. And he graduated in MIT, BS in mathematics. He took a series of jobs related to computer security. He became interested in the key distribution problem. He goes up to Watson Labs, and he learns that a fellow named Marty Hellerman had just given a talk on the problem of key distribution. And Whitfield did a lot of work for Sun Microsystems and now is retired. So Marty is another Bronx boy. I told you I spoke for Bronx English. So Marty's graduates from NYU, gets his MS and doctorate from Stanford, works there at the Watson Research Center. Then he goes out to Stanford, and he's emeritus professor since 1996. So Diffie drives across the United States to work with Hellerman. So they study the key distribution problem, and they were joined by this fellow Ralph Merkle. So he comes up with the idea of asymmetric key cryptography, also known as public key cryptography. Easier maybe is two-key cryptography. So there's two keys, a public key and a private key. So the public key gets published in a telephone book. So you can go out and find the telephone key, the public key for anybody on the web. But you have a private key, and the two keys are what make for public key cryptography, and it does away, quote unquote, with the key distribution problem. So the lockbox analogy is what Diffie comes up with to say, this is what will help you break this code. It gave him the idea that there was going to be this public key cryptography possible. Okay, I take a secret and I'm going to mail it to you, so I put it in a box, I put a chain around it, I put a key, a lock on the chains, and I send it to you. You put a chain on the box with another lock, and you send it back to me. I take off my lock, I send it back to you. You take off your lock, and you got my secret. So from that physical sort of, I used to have a puzzle called the cannibals and the priests puzzle in mathematics. That kind of puzzle, Whitfield said, I can come up with public key cryptography. But he didn't come up with a workable implementation. He knew higher level math would be involved, but he didn't have it workable. So then Rivest, Shamir, and Edelman are the ones that come up with it. And they come up with code that's known as RSA, named after their first initials. So it involves mod calculations. And it's the first of the one-way functions, or what we call one-way functions with a trap door. So this is published, and Marty Gardner, who was a famous writer of sort of public science papers, he issues a challenge, says, can you break it? And he's going to give him $100, and it took 17 years before the ciphertext was broken that went to make up the RSA code. So going back, in 1994, a team of 600 volunteers said that they'd broken the ciphertext, and then something called the Coca-Cabana was built at $10,000 that said they could break ciphers such as DES. So again, we come back to Great Britain and say, oh, we did it before you. And again, this business of competition and, you know, we did it. And so they have people by the name of James Ellis. He said that he did this, worried about it, and he came up with essentially RSA a long time ago. But again, people in governments don't release their findings because they don't want the enemy to know that they then broke their code, because they may need to break their code again. So then these other people get involved and follow up on Ellis's work, and they claim that they did public key cryptography. So now we come to Phil Zimmerman, another Zimmerman in the crowd, and he builds something called pretty good privacy. And essentially he didn't do something that was so unique, except he made a system. He had many of the existing codes and he put that together. And again, NSA is on his back, the United States government people are on his back, and he uses Usenet to publish the code for pretty good privacy. And it took off because, and he's trying to break the security part of the problem. He's trying to say, I want to protect everybody's privacy, so I'm going to give you something called PGP so you can keep things private. So he develops this system which lets you do that, and it is used. MIT, Harvard, Stanford, a lot of people use pretty good privacy among faculty when they do certain kinds of evaluations of other faculty that they want to keep secret. So these other people used it, and it became a pretty good system. So there's books written about it, and he's persecuted also for his work. So now I come up to, we've got public key crypto, RSA, Diffie-Hellman, and they all use integer mod or polynomial arithmetic with very large numbers or polynomials. And the problem of breaking it is the difficulty of reversing exponentiation, or defining discrete logs, or finding the prime factors. The ones you probably most heard of is factoring a prime. I mean, not factoring a prime, taking a number and finding its prime factorization. So there's a fundamental theorem in numerical analysis that says that every integer can be broken down into a product of primes to its respective powers. But the problem, it's one thing to take two numbers that are primes and multiply them together. It's another thing to get the number and find the primes that go to make up that number. One is an easy problem. Multiplying p times q is no problem. Finding what p and q are if I give you n, especially when they're very large numbers, that's another problem. So this is the kind of thing that we did. This kind of mathematics is what makes up most of the various crypto schemes before elliptic curves. So now elliptic curves come onto the scene. So first of all, an elliptic curve is not an ellipse, and that causes people trouble to begin with. And elliptic curve theory came into being in the 19th century because it's these kinds of equations that tell you the length of the arc of an ellipse. And the scientists in the 19th century wanted to know where to predict the path of planets. So they needed to find the length of the arc of an ellipse. And so they got into these equations. So the equation, one form of it, a simplified form, is y squared equal x cubed plus ax and b. And these are all real numbers. And they defined another point called O. And they can define addition on this elliptic curve. So it's amazing that they come into all of this, but they do. And so this is the curve y squared equal x cubed plus x plus 1. So this would be called E11, 1 comma 1. The coefficient of x is 1, the constant term is 1. So this is the graph of E11. So you take 2 points on that graph, P and Q, you create the secant line between P and Q. It intersects the curve at that point, P, that's labeled PQ minus, and you reflect that curve in a symmetric axis going through through the central point there, and that becomes P plus Q. So that's the geometric interpretation of P plus Q in elliptic curve geometry. It's an oddball definition of P plus Q, but it is the definition of P plus Q. Like math, don't ask me why, that's the answer. That's what P plus Q is. So we're dealing in cryptography, so we're not dealing in the real numbers. So now we have to move, and mathematicians think about this, oh, supposing we didn't work in the field of real numbers, supposing we worked in finite fields. So there's two families, you still have the A, B, but you subscript it by P if you're going to talk about fields over the field ZP. Z is the German for Zahlen, and P is the prime. And then you use integers modulo a prime in your elliptic curve activity, and this is best in software. And then if you have E sub 2m AB, that's defined over the Galois field that should be m, 2 to the n. So you use polynomials with binary coefficients to do that kind of thing. So there we moved from reals to integers again. So this is a Mickey Mouse slide, but it gives you an idea of showing that something's on the curve. So this is the curve. You still got the y squared, you still got the x cubed plus ax plus b, but you got it mod p on one side and mod p on the other. So we want to show that the 0.95 is on that. So you see the prime 11 is subscripted, and you got 1 and 2. So we're talking about y squared mod 11 equal x cubed plus 1x plus 2. So we want to show that 9,5 is on that curve. So y squared is 25, mod 11 is 3, 11 times 2 is 22, 3 remainder. On the other side, I have x cubed, which is 9 times 9 is 81, times 9 is 729, plus 1x, which is 9, plus the 2, which gives me 740, and you do the arithmetic, get 3 on the others on the curve. So I got a point on the curve, an integer on the curve. Now I got to compute what's 9,5 plus 9,5, because I want to find the other points. The point is, but this is, I've got to find other points in this field. And so we got to find rules for adding points together. So So these are the rules for E sub P A B. So what you do is, these are the first three we're not going to be concerned with, but we'll talk if